In an earlier video, we talked about the average rate of change of a function. And just as a quick reminder, what that did was it found the rise over the run, or the rate of change between one point on a function and a later point on a function. And we talked about how it didn't really matter so much what was happening between those points, but what the average rate of change was. An example would be, if you had two people who got in different cars and finished across a finish line at the same time, then no matter whether one driver started off slow and then sped up towards the end, or another driver started off very, very quickly and then slowed down at the end, as long as they traveled the same distance over the same amount of time, their average rate of change would be the same, right? Their average rate of change. And this holds true not only for velocity, but also, financial problems or temperature problems or whatever. The average rate of change requires 2 points, so that you can determine a rise over run between those 2 points and get the average rate of change. Now, in this video, we're going to talk about something called an instantaneous rate of change. For this, you do not need 2 points, you just need 1 point. So you might want to know the instantaneous, and that's a good word, instantaneous rate of change right here at this value of C, right here. And we'll talk about how to find that in just a minute. Recapping an exercise that we did in the previous video and some of the results we got. If this is the height of a coin that you're going to drop off of the top of a building, this happens to be not the Empire State Building, the Washington Monument, which is 555 feet tall, then this would be its height after a given time. And so it starts off at 555 feet when t is 0. But then as t changes to 1 or 2 or 3, you start subtracting quantities away from 555 as it falls, and the height obviously decreases. After some algebra, and you can watch the video to see how we got these, the time it takes to hit the ground is about 5.89 seconds. And we found that by setting the height equal to 0 and solving for t. And we talked about the average velocity on the entire interval from 0 until it hits the ground after 5.89 seconds. And that wound up being negative 94 feet per second. That's a velocity, rise over run, feet per second. And you notice that's a negative quantity indicating the coin was falling. But if we looked at the average velocity on just the last second alone, if you look at the graph here, you can tell this is going to be much, much steeper. And we know that intuitively because the coin will be falling faster as it accelerates due to gravity. Okay, let's get back to instantaneous velocity, and then we'll look at that example again. All right, the instantaneous rate of change of any function, it doesn't have to be velocity, is found by taking the function's derivative and plugging in, whatever value you're looking at, C or 7 or 10 or 5 or what have you. And we know that once you've studied derivatives, that derivatives tell you the slope of a curve specifically at a particular place, not over a range of numbers, but at a particular place. So instantaneous rate of change uses calculus, where an average rate of change just uses old algebra, rise over run. So as long as you know how to differentiate and you know what derivatives are, you can determine the instantaneous rate of change of any function at any given value. So let's try this example again very quickly, and we'll compare it to some of the answers we got previously. All right, what's the instantaneous rate of change of this function, this height function, dropping a coin off the top of the Washington Monument at 0, 1, and 5.89 seconds? And we'll interpret what these answers mean. So when I see the word instantaneous rate of change, I know I'm going to need the derivative. So I use my derivative rules to differentiate this guy, and it would be negative 32t using the power rule, and the 555 goes away because the derivative of a constant is 0. So I'm going to plug in 0, 1, and 5.89 here. So the instantaneous rate of change at 0 would be 0. Now, is that intuitive? Well, let's think. All right, you have the guy standing at the top of the Washington Monument. He's holding a coin. The second as he's letting it go, he hasn't already let it go. It's still in his hand, or he's in the process of letting it go. At that instant, it's not falling, so the velocity would be 0. The instantaneous rate of change of height would be nothing. All right, it's not falling yet. But 1 second later, we can plug in 1 into the derivative. We get negative 32. It's sped up in that first second, and now it's falling at 32 feet per second downward, so that'd be negative because it's a downward velocity. And then you can tell after 2 seconds it's negative 64. It speeds up even more, et cetera, et cetera. This is the gravitational constant on Earth. Everything falling due to gravity accelerates at negative 32 feet additional every second. So we say negative 32 feet per second squared is the acceleration due to gravity. But in any case, at 5.89, this is the second it slams into the ground. We're probably going to need our calculator for this one. We'll take 5.89 and plug it into negative 32t. So negative 32 times 5.89. And we get negative 188.48. Negative 188.48 feet per second. And this was feet per second. And this was feet per second. Okay, so we get those units there. And let's compare this to our previous answers here and see if this makes sense. First of all, the average velocity on the entire interval on average was negative 94. This makes perfectly good sense. Earlier in the fall, it was slower. It wasn't going very fast yet within the first second, and towards the end, it was much faster than that. Moreover, if you look at the average velocity in just the last second alone, it was negative 172 feet per second, and at the second of impact, the instantaneous rate of change was negative 188, which is even faster than the average velocity over the last second. So this is just one application. Don't think that this is the only time that this is used. You can also use this instantaneous rate of change concept for financial problems, profit growth throughout the calendar year, population growth of a society, or population growth of bacteria in a petri dish, on and on and on. There's so many examples you can look at instantaneous rate of change, but hopefully this example here helps you kind of piece it together in your mind.